Here we'll describe what solubility is and how it's affected for both gases and solids. Solubility is described as the maximum amount of material that a solution holds before it can no longer dissolve any more material. If you want to think about it as having a pitcher of water and adding sugar to it, how much sugar you can add before the sugar stops dissolving and goes straight to the bottom. Solubility of a molecule is influenced by the strength of the solute-solvent interaction. That is, it's controlled by intermolecular forces. Solutions are described as being undersaturated solution when it's still capable of dissolving material. That is, it hasn't reached its saturation point. The saturation point is when you have the maximum amount of material dissolved into the solution that it can hold. And the only way you could dissolve more is by either adding more solvent or by increasing the temperature. Temperature has the effect of generally increasing the solubility. Increase the temperature, dissolve more material in it. There are a few exceptions to this, but the general trend is true. We can also create something known as a supersaturated solution. A supersaturated solution is a solution which has more material dissolved in it than it's supposed to. And it's the result of having a saturated solution at a high temperature, and that solution gets cooled off. Well, as it gets cooled off, oftentimes the solution won't actually cause anything to precipitate out because it's still dissolved in solution because of those intermolecular forces. And only by adding a crystal seed can we actually get a supersaturated solution to crystallize almost instantaneously. So when we describe our solutions, we have our undersaturated solutions, which we're typically used to working with, saturated solutions, which have the maximum amount of material that can hold, and then supersaturated solutions, which we rarely work with. So those are the factors that control solid solubility. Let's talk about liquids dissolved in other liquids. When we have liquids that are dissolved in other liquids and they form homogeneous solutions, we describe the liquids as being miscible. That is, you can't tell one liquid apart from another. However, like oil and water or hexane and water, these are examples of immiscible liquids. They don't mix well, and so they form their own phase that's distinct to it. Because things like water and hexane have very different intermolecular forces, this explains why they don't mix well. Water's polar, hexane's nonpolar. This is important in biology for the fact that we often have vitamins which are described as being water-soluble vitamins, like vitamin C, or vitamin A, which is a fat-soluble vitamin. Water-soluble vitamins you can take as much as you want, and it will just easily be transported out of your body if you have too much. Fat-soluble vitamins, however, need to be a little more controlled because they dissolve in fat readily. They are only really utilized when that fat is burned, and so you can build up too much vitamin A in your body and actually have it be detrimental to your health. Gas solubility is something you're probably familiar with every time you open a can of soda. Gas follows something known as Raoult's law. Increasing the temperature of a solution with a gas in it decreases the solubility of the gas, while increasing the pressure of the gas above the solution increases its solubility. You can see that in the two plots here. The plot on the left, the pressure on top of the solution on the x-axis increases with the solubility of the gas. On the right, we can see how increasing temperature decreases solubility. Temperature decreases solubility because as temperature goes up, gas molecules have more energy and therefore they are more likely to reach the surface and escape.